else, but at least I'll try to explain why I think many of these things that are called mysteries are not really mysteries at all. An extremely precise and sophisticated measurement of the expansion of the solar system was made by the Americans, by NASA. And the correct number is 1.5 centimeters per year. And this is completely due to the loss of the mass of sun due to its radiation. So actually this experiment shows that there is no expansion of the solar system. So this is my definition of quantum mechanics. I'm sure most of you are not physicists, but basically the simplest way to define quantum mechanics is that if you go to small enough things or high enough energies, you will have to modify the laws of physics. And this is an experimental fact. And this was, of course, a big surprise, I guess, in the late 19th century. So physics is an empirical science at heart, right? Like Richmond Feynman says, it doesn't matter how smart you are, it doesn't matter how beautiful your theory is, if it doesn't agree with the experiments, it's wrong, okay? And this is what quantum mechanics is about, it agrees with the experiments. These are the famous people. The last one on the right-hand side is Paul Dirac. This is one of the few equations I'm going to show because it's called the Dirac equation. It's a relativistic equation for quantum mechanics. And it is one of the most beautiful results in the physics of the 20th century because he actually derived this result by just based on symmetry and conservation laws, exactly what Larry was talking about. So he showed that at least in this, for many systems, symmetry and conservation laws actually precisely determine how the physical systems behave, and it can be put in a mathematical form. This is called the first quantum revolution because, of course, once we understood the existence of atoms and electrons, we could build devices based on them, and that's what we have today. There's a difference in technology that's being now conceived. Let me just say that why this is called the first quantum revolution is that these devices that we have they're fundamentally quantum mechanical, like the transistors and diodes and things like that that make up computers. But actually they don't really use quantum mechanics directly. The essential features of quantum mechanics are not used in these devices directly, or these devices don't exploit quantum mechanical features explicitly. Another way of putting that is that these devices can be often modeled with some simple classical equations. So, like if you look at the flow of the current in a circuit, the electrons are quantum mechanical, but the current can be described by a simple macroscopic current. You can write very simple equations without any quantum mechanics and explain how the current flows from one place to another, right? So in that sense, these devices are not exploiting quantum mechanics. So what I'm going to explain at the end is that now we are building devices that actually specifically exploit quantum mechanics. Then I have to define what is quantum mechanics, so let's define that more precisely. So what is it that makes up quantum mechanics? I mean, if I make a poll here, if I had time, I would come and ask, well, what do you think is quantum? I mean, what are the signatures of quantum mechanics? What is it? When is something quantum and when is something not quantum? Now, there's several things that have been defined to be quantum. There are a couple of them here. There are many more. The most well-known ones are the interference effects. So this is what Larry was talking about. So you will get this pattern from two slits, whether you shoot light or electrons or any other objects, quantum mechanical objects through these slits, they will make a wave pattern. So there's this particle-wave duality. That's one of the things that initiated quantum mechanics. This needed to be explained. So that's called interference. Actually, all waves interfere. You can see this on a lake. If you make waves in two different places and they meet, you can see that they can either cancel out or enhance each other, okay? The second one is called wave function collapse. That's a bit more technical, but the point is that in this picture, the particle is not, if I have a particle that's described by this wave function, a quantum mechanical object, it's not in one place. at any given time, but it's sort of spread out. Its wave function is spread out. But if you measure it, if you make a measurement, you can precisely pinpoint where the particle is after the measurement. And this is called the wave function collapse. So in the wave function picture, that means that the particle position collapses to a well-defined point in space. And that's the answer that you will get from the measurement. So these are the two typical signatures of quantum mechanics for single particles. But it turns out, in fact, and this is really interesting because this was shown last year. Okay, so we're not talking about 1930s, we're talking about last year. Okay? That in fact, if you take just a single quantum particle, just one particle, okay, that is quantum, or one quantum system with d levels, all its quantum mechanical, what we call quantum mechanical properties, can be classically simulated. That's what this picture is about. It's a technical thing, so I will not go into the details, but one can construct what is called an interference circuit that is completely classical, that gives you the same results as if you were to measure quantum mechanical particles, single particles. So one can actually say that single particles do not exhibit any quantum mechanical phenomena, in the sense that all the things that we think as quantum mechanical for single particles can be simulated by classical but stochastic, probabilistic methods. Okay? So the real definition of quantum is something that cannot be simulated by classical, stochastic, or probabilistic methods. And for that, you need more than one particle. And for that, you need entanglement. I know this word entanglement also is very confusing because this is used from anything to, from insects to humans to whatever. It has a precise meaning in quantum mechanics, but you can think of entanglement as the word says. It is combining two things into something that's more or different from its parts. Okay, as you can see somehow in this picture. So when you combine two or more quantum systems, and if they entangle, that means that they become a new whole. Okay. That is different from having two separate quantum systems. And now the point is that if you separate these two systems, when they have been entangled, they will not go back to the old parts, unless you do something to them, okay? They are so-called correlated. So in the professionals, we use the word correlation, okay? So there is quantum correlation between these two parts of the system once they have been entangled. Before that, not. But if you entangle them, and then you separate them, they are no longer the same individuals that they used to be, but they are actually a combination of half of the combination. And in this way, it's really easy to understand the spooky action at the distance, right? So what is that? So this is the thing that prompted Einstein in 1935 to say that quantum mechanics is incomplete, which is a polite way of saying it's wrong. See, he concluded that this is impossible. So if this happens, this is predicted by quantum mechanics, but it doesn't make sense. So if it happens, then quantum mechanics must be wrong. So the key is in this entanglement, again, like I just said, again, if you take two quantum systems, spin up and spin down, once you combine them, they are no longer a combination of spin up and down, but something different. And when you separate them, and don't perturb them, just leave them alone, the separated parts are not spin up and down. It's a combination of the spin up and down. There's a quantum correlation, right? I mean, it's like if you mix two fluids and you put half of the fluid in another jar, that's not going to be the, say, yellow and black. It's not going to be the yellow or the black. It's going to be a mixture of the yellow and the black. In the same way, once you have entangled these systems and you separate them, they're no longer the same as they used to be, unless you do something to them. And then you decide what values they take. And so this is the famous non-locality measurement. I should say that this word, again, non-locality is confusing. There's nothing non-local in quantum mechanics. This non-locality refers to the fact that if you try to explain this classically, you have to introduce the idea of non-locality, spooky action at the distance, which is impossible, or at least doesn't make any sense. But in quantum mechanics, this is completely natural. There's no mystery. Like I said, once you mix these things, they're not going to be the same as before, except when you force them to be one or the other, right? So this experiment has now been repeated many times, simply because this is where they made absolutely sure that there was nothing that could spoil the experiment. This experiment sounds simple, but it's actually very delicate, because quantum systems are so delicate. So they actually did an extremely careful plan of the experiment so that what they measured would not be affected by anything that they could not control. So what is the idea here? They have this entangled systems spins, in this case, in this central building, and then they separate them very carefully, not to perturb them, to keep this correlation, and then they send the two parts in two different places. And then they make a measurement on one place. And that immediately determines the value of the spin in the other place. And that proves this feature of quantum mechanics. Last year, the Chinese and the Austrians did another experiment repeating this with satellites. So the distance they made this measurement between Peking and Vienna, where the distance is thousands of kilometers. So there's no way that information could be passed between these two places by any means. So this really proved, well, this experiment already proved, and earlier experiments, that quantum mechanics has this feature of quantum. I would not use the word non-locality, that's not a good word. I would use this persistent quantum correlation. So if you think about it, there's really nothing mystical about this. It's just correlation. Something that we don't see in everyday life, but we don't live in the quantum world. Okay, now let me speculate, since there have been a lot of speculative talks here today. So everything I said so far is a scientific fact, based on experiments, okay? As physics should be. But there are a couple of interesting proposals recently. I just want to mention to inside your imagination, this is complete speculation. But again, it's based on experiments, in part. It's based on theory, but experiments mostly. So there is a proposal or an experiment that the origin of time is due to quantum entanglement. So they made a very simple measurement of an entangled quantum system and showed that unless you entangle yourself with this quantum system, then there's no dynamics, there's no evolution of time. So it doesn't prove anything really, but it does suggest that it's possible that time is not an absolute coordinate, but it's an emergent quantity from quantum mechanics. So fundamentally, the time in the universe could be due to quantum mechanics and not an independent variable. Again, it's pure speculation, not a proof, but an interesting idea. Physicists are always open to new ideas. There's even a higher level of entanglement, and this is actually based on mathematics. It has been shown in several cases that if you have something technical called a conformal field theory on a d-1 dimensional surface, like a 2D surface, then you can reduce that theory to a general theory of relativity in the higher dimensional space, in the so-called bulk, in the d-dimensional space. That's a really interesting idea, because this would say that also the force of gravity is not a fundamental force of nature, but it also emerges from quantum mechanics. Maybe, maybe not. We certainly know that the other forces are fundamental, but it's possible that gravity is not a fundamental force. For the other forces, we found the mediator particles. We know how they work. We understand these forces. But for gravity, we don't. We only have the classical theory of gravity. Okay, so again, speculation.